under the joint supervision of Professor Peter Biko and myself. And right now, Rachel is a faculty member in the School of Mathematics and Statistics at the University of Sydney. So today her talk is about global community detection. Thanks, Rachel.
Thank you, Haiyan, for the very nice introduction. And thank you everyone for coming to the first talk in the morning. Yeah, so it's my great pleasure to be able to give a talk at this workshop, which is also celebrating Peter's belated 80th birthday. So I'm going to talk about some recent work with my collaborators, Xiao Han from University of Science and Technology, China, and Xing Tong from USC. On partial information networks. So statistical networks is an area which Peter and many of you here have made a lot of fundamental contributions to. Don't know why that, okay, it's not on my screen. Yeah, so Peter and many of you here have made a lot of fundamental contributions to the area of statistical networks. And I was very fortunate to be introduced to this area when I was a PhD student here. A network, which doesn't need much introduction for this audience, is just a graph with nodes and edges. We're talking about social networks here. So the set of nodes represent a set of individuals indexed from 1 to n, and the edges represent some kind of relationship, friendship, interactions among them. And in the simplest case, these are binary and undirected edges. So what are some of the statistical problems we are interested in? We can estimate the latent community memberships, right? And communities are groups of people more tightly connected with each other than with the rest of the network. And this will also be the focus of our work. So these communities can be, people graduated from the same high school, people sharing a common interest, and so on. We can also estimate the number of subgraph counts. So we can count the triangles, wheels, stars in the network, and they tell us something about the connectivity patterns in the network. We can also do inference on node covariates. So they tell us something about the personal traits in this case. So most of the current work assumes you either have a global view, so you have access to the whole network, or you have some edges missing at random in the network. Or you can sample multiple subgraphs from the whole network and then combine information from them to infer, say, global community structure. And Peter, Puna, and Shumendu recently had a very interesting paper on this approach, patching together information from multiple subgraphs. But the question is, so as an individual in the network, I often need to make decisions based on my local view of the network alone. Right, so for example, I need to decide whether I want to share a piece of information with someone else. And the decision is based on which friend circle or social circle that person belongs to. And at the same time, I don't have the full network view. So the question is, as an individual in the network, how much of the full network do I get to see? So in the first layer, I know who are my friends, right? These are the people directly connected to me. So I see these edges. And I probably also know who are my friends' friends. And for most of us, that's probably the extent of our social knowledge. That's for me, this is going to be the extent of my social knowledge. Any edges further away from me, I'm not going to see them. So it is definitely possible that some people can see further away from the center. But the key point is, if I take an individual as the center, whether another edge in the network is observed by that person or not depends on the distance from the center. In other words, the path length, if I start walking from the center. And this is what motivated us to think about the setup, which we call it individual-centered partial information network. And here's just a toy example illustrating, making the idea more concrete. So we have 6 individuals and this toy network connecting these 6 people on the leftmost panel. And now let's say we take individual 1 as the center, and we will use L, this capital letter L, to denote what we call knowledge depth, which is essentially just path length from the center. So when L is equal to 1, this person just see a star around them. When L is equal to 2, they get to see almost the full network on the left, except for this edge between 5 and 6. And they don't see this edge because this edge lies on the path of length 3, starting from the center. And when L is equal to 3, I recover the full network. So the idea is that we're going to characterize the amount of partial information or local information perceived by individual 1 using path length, and we call it knowledge depth. And this is denoted capital letter L here. So we're going to focus on the value L equals 2 in this case, because as we know, as long as the network is not too sparse, even the moderately large L is going to return almost the full network. So that's not very interesting. And L equal to 1 is not very interesting either. It's just a star. So maybe L equals 2 or L equals 3 will be the most interesting cases. And we're going to focus on L equals 2 and leave L equals 3 for future work. Okay, so the question again is that we want to infer global community membership just using this partial information for L equals 2. So of course, the structure of our partial network is related to many popular network sampling schemes in quantitative social science, so including egocentric sampling, snowball sampling, respondent-driven sampling, RDS, and so on. So all these sampling methods work by first choosing some seed nodes and then ask them to recruit their neighbors in some sense. Right. So in egocentric sampling, you take the center and then recruit the neighbors and look at the connections between the neighbors. And snowball sampling and RDS do this in waves. Right? So you first ask them to recruit their neighbors and then ask the neighbors to recruit their neighbors. And this waves of sampling continues until you have reached a desired sample size. And RDS, you can also do probabilistic sampling and you have a weighted average of those samples. And the main difference between our conceptual framework and this one is that we are interested in what one instance of the partial network can offer. And at the end of the day, we are interested in comparing what network structure is visible to each individual. And most of the RDS methods are focused on estimating node covariance, but we are interested in latent community structure. And in some special cases, you may not get to sample multiple subgraphs from a restricted network. So coming back to the setup, we have this graph with nodes and edges. And as usual, we'll use the adjacency matrix to represent this symmetric undirected network with an edge. So Aij is equal to 1 if there's an edge connecting nodes I and j. Now we are going to use the matrix B to denote individual 1's perceived adjacency matrix based on L equals 2. And without loss of generality, we are always going to assume we are centering at individual 1, because if you're interested in any other individual, we just permute matrix. Okay, so back to this toy example, here's my matrix A, the full adjacency matrix, and this is my matrix B corresponding to this middle panel here. So the only difference is between individual 5 and 6, this edge I don't observe in B. In general, we can represent the relationship between A and B like this. An edge between I and J is observed by this individual 1. Right? It shows up in matrix B if and only if at least one of the IJ nodes is a neighbor of individual 1. So here, this edge is not observed because neither 5 or 6 is a neighbor of 1. More succinctly, we can represent this relationship using a matrix relationship. So B is connected to A through this S matrix. S matrix is a diagonal matrix where the entries represent, they encode whether an individual is a neighbor of individual 1. So before I dig into the theoretical, Peter, you had a question.
So Zachary's karate.
Oh, yes, yes. It's a bit cliche. Yes, so before I dig into the theoretical analysis, I want to sort of present a teaser kind of result on the Zachary Karate Club, which we all know and maybe we are too familiar with. But the point is, even with this very well-analyzed, well-studied network, using our method and framework, we can still get some interesting observations. So here's the network itself. If you haven't seen this before, this is the social network relationship between among members of a karate club. And then there's two hubs in the network. There's the node H and the node A. So one of them is the instructor and the other is the administrator. And the network split into two communities after dispute between these two people. This is the network itself with two communities. And here I have selected some individuals, including the two hubs. And I take their own partial information network. I take each one of these individuals at the center and look at the partial information network and try to do global community detection. And this is the accuracy I get in the end. And I will talk about the algorithm later. And the first row shows the degree, how many people they are connected to. And this is the fraction of edges they observe in the full network. So we can see that these two nodes, the two hubs, in fact, don't have the best performance. They don't perform as well as, say, individual 20 and individual 32, who both have fewer edges than the two hubs. Right? And especially individual 20, only 3 degrees and 50% of the edges, and they almost have a perfect answer. So a closer look at this connection, we see that 20 so out of the 3 degrees, 2 of them are connected to the hubs. Right? So this is sort of saying that you don't need to be the most important person in the network. You just have to be connected to the important people in each community. And we will try to illustrate, we will try to capture this message with our theoretical analysis later under the block model setup. The general analysis, we did it under the generic low rank assumption. We assume the population matrix has rank K, and then it has this usual eigenvalue, eigendecomposition, and D is the diagonal matrix of different eigenvalues, and V is the corresponding eigenvector matrix. So D and V are population quantities, and then A is generated independent Bernoulli from the population. So we all know that the usual theoretical analysis proceeds by decomposing A into the signal plus noise, right? And the signal is the population version and the noise is the fluctuation. So we don't get to see A, we get to see this partial adjacency matrix B instead. So the question is, what is the signal term here for B? So it turns out the signal term here, which we denote by B sub E, has this particular form. So it is not the expected value of this whole thing. It is not the expected value of the individual terms. In fact, expectation is only applied to A and the S is left as a random quantity outside. So this signal term is a random term. And the reason is there's a S square term here, and S is the diagonal matrix of Bernoulli random variables. So if you square Bernoulli, you still get a Bernoulli, but that's much bigger than square of the expectation, the P square, which gets small when P goes to 0. And it's a signal term of the B matrix in this sense. If I look at the spectral norm of the difference, it's smaller than or equal to the smallest singular value of BE. So next, I'm going to talk a little bit about the theoretical properties of BE, which allows us to do spectral clustering later. So if I assume these two matrices are invertible, then I can show the rank of BE is exactly 2K. And furthermore, if I index the eigenvalue eigenvector pair from -K to -1 and then 1 to K, then this eigenvalue eigenvector pair has the following form. So so I need to first construct a matrix here, H. So H, so X here is a scalar quantity, and H depends on the population quantities D and V. Right? These are coming from the eigendecomposition of the population matrix, as well as the S matrix. So after I have constructed this H matrix, I look at the determinant equation and set it to 0 and find all the solutions to this determinant equation. And it turns out the inverse is one of my eigenvalues of the BE matrix. And for the eigenvector has two parts, the sum of two parts. So I construct the first part, Q1, by substituting in the corresponding eigenvalue and find an eigenvector corresponding to the 0 eigenvalue here. That's the first part. And the second part is linked to the first part by this equation here. And then I connect the two by multiplying the S and the I minus S. So intuitively, S picks out the neighbors, the rows corresponding to the neighbors of individual 1. I minus 1 picks out the non-neighbors in the rows corresponding to individual 1s. So I put all these Q's together and call this the big Q matrix. And the big Q matrix consists of two parts, the neighboring part and the non-neighboring part. And I can further orthogonalize this system. So I get this, so Q can be, the little q can be chosen such that the big Q becomes the orthonormal matrix. So we can derive further properties on the eigenvalues of the signal term BE. So let Pn be the maximum probability, connection probability. And here it's just saying the neighbors of individual 1, that edge density behaves like Pn. And then I have the usual log n lower bound on Pn. Then this is, we can get more details on the eigenvalues in the following sense. So first of all, the orders of these eigenvalues behaves like this. And if I let Pn go to 0 and with some additional constraint of the eigenvalues, we can obtain high probability expressions of these eigenvalues. So exactly k of these eigenvalues are positive and the other k of them are negative. So for the purpose of spectral clustering later, I don't need to know these high probability forms of eigenvalue. I just need to know the order. However, a closer look at these high probability expressions gives us some interesting observations. So it turns out if I call this lambda mean, this is the smallest eigenvalue of this matrix here, VTSV. It determines the gap between the smallest eigenvalue in magnitude, so singular value, and 0. And we know that this gap influences how well you can do spectral clustering later. So lambda mean drives the signal behind the spectral clustering. So just a quick summary of the theoretical properties I have showed so far. So first we derived this eigenvector matrix Q, and it consists of two parts, the neighbors of node 1 and the non-neighbors of node 1. And we derived the order of the eigenvalues. And we have this quantity, this eigengap here, lambda mean, determines the signal strength of spectral clustering later. And since lambda mean influences the performance of spectral clustering, we can think of it as a centrality measure for individual 1. And it's a centrality measure in the sense that it assesses individual 1's awareness of the global structure. So it tells us how important individual 1 is, determining the overall global community structure. So we are proposing this as a new centrality measure. It turns out the lambda mean naturally lies between 0 and 1. And even though we don't know V, this is the population quantity, the population eigenvectors, we can estimate this using the empirical version of A. So we have an empirical version of lambda mean. And we can show that when k is equal to 1, lambda mean bears connections to the degree centrality and eigenvector centrality. So it's in fact a combination of both pieces of information. Big K is the low rank assumption, is the rank of the population expected value of A. Yeah. Oh, sorry. Okay. Thanks for the question. Okay, so now we're going to do some concrete calculations of misclustering rate on the usual block model setup. So we first consider the simple stochastic block model where the population version can be written in this form, where so P is the K by K connectivity matrix, and pi is the binary membership matrix. N by K binary membership matrix. And then the connection between node I and J, the probability of connection is entirely determined by their membership. So I don't get to see A, I get to see B. And we can show that, in fact, in the Q matrix, which is the eigenvectors of the BE, the signal term of the matrix B, there are exactly two types of rows in Q. Even though we don't get to see Q, and this is the usual business with spectral clustering, we get to see an empirical version of B. We get to see an empirical version of B, which is B. So we can cluster the W, the empirical version of Q instead, provided P, the Q and W are close enough, and there's enough signals between the different types of Q to separate the nodes. And this is what we are trying to capture with this lemma here. So Pn is again the maximum connection probability. And here I'm just saying, so here I'm assuming without loss of generality, individual 1 always belongs to community 1. Then this Pn again is the edge density around the individual 1. And then some usual assumptions on the size of each community and the minimum singular value of the K by K connectivity matrix. And here's the lower bound on the edge density. Then we can show there are two K types of rows in this matrix Q, and there are 3 cases. When node I and J don't belong to the same community, then their corresponding rows in Q are different, and their lower bound, the difference is lower bounded by this. If I and J belong to the same community, but exactly one of them is a neighbor of individual 1, then the corresponding rows in Q are different again, and they're lower bounded by this. Only if they belong to the same community and either they are both neighbors of individual 1 or they are both non-neighbors of individual 1, then these rows will agree. So there are exactly 2 K types of rows in here, and K types of rows in the neighbors and K types of rows in the non-neighbors.
That Pn is larger than local. Now suddenly I found out about square.
Yes.
So where does this difference come from?
Yeah, so this is coming from the fact that we only have access to B, which is not the full A. So you lose a lot of edges in the matrix B. And you can actually see this from the order of the eigenvalue here. So usually this is n times Pn. So we have another factor of Pn to the half here. So that's where it's coming from. So the signal here is just a lot smaller compared to the full. Yep. So from that lemma, now we have this clustering algorithm. We're going to treat basically the neighbors of 1 and the non-neighbors of 1 separately and apply some kind of clustering algorithm to put these two groups of individuals into K groups. So after we do K-means on each group, then each clustering is going to return us a cluster with, so it's going to return us a group of K clusters, right? So I have 2 K clusters in total from the neighbors and from the non-neighbors. So the next step is to merge them into K communities. And we know that this clustering only gives us labels identifiable up to permutation. So we need a way of merging. And then the way we merge it is that we construct 2 estimates of the K by K connectivity matrix. So the first estimate is constructed by looking at neighbors of individual 1, right? And I do a sort of frequency count and estimate this P. And this one is estimated by looking at, so one of them is a neighbor and the other one is non-neighbor, the rectangular part, and I get another estimate of the P. And then I try to match the 2 by minimizing the Frobenius norm and find the most optimal permutation to merge the 2 groups. So using this algorithm, we can show that if my Pn is lower bounded by this, then I achieve weak consistency and this is the upper bound on the misclustered node. Now we notice that we lose a bit more here because of the merging step, because when we construct these two estimates, the P here, we need some concentration properties, and that's the reason for this even higher lower bound. So we can extend all of this to a degree corrected block model. And so degree corrected block model allows us to describe some sort of individual specific features. In particular, it's the degree heterogeneity. So here we're using the theta matrix. It's a diagonal matrix where theta I is the degree parameter associated with individual I. And the population version looks like this. And when you look at the connectivity between I and J, you just get these extra theta I and theta J at the front. And for ease of analysis, we're going to assume the theta I are ID random variables generated from a certain distribution, and the mean of the distribution behaves like a constant. And so it turns out we can have a very similar clustering algorithm for the degree corrected version. So here again, I divide the nodes into the neighbors and non-neighbors. And to account for degree heterogeneity, we use the standard approach in Jing and Alexandrov's paper, which is to divide out, to normalize the rows by the, to normalize each row, and then find the centroid that minimizes this 2-1 norm. And again, we have a merging step, but this time we need to account for the degree parameters as well. And it turns out we can also have a similar consistency, weak consistency result for the degree corrected case. So we notice that in all of the above cases, our upper bound on the misclustered node doesn't depend on, it's uniform for everyone. Right? And this is because we did everything in the exchangeable setup. So we can't really tell the difference between how everyone can do in terms of global network detection. So we considered a conditional setting so that our clustering error bound can reflect the neighborhood feature of individual one. And also we introduced another setup, which is that the degree parameters are generated from a two-component mixture model in the following sense. So there's F1 and F2, and the mu2 is the mean of F2 and mu1 is the mean of F1. So mu2 represents the degree parameters for the hub nodes, and mu1 is the degree parameters for the non-hub nodes. So there's two types of nodes in my network. And then I just need one more notation. So NJK is counting the number of individuals who are neighbors connected to individual one, and J denotes whether they are a hub node or non-hub node, and they belong to community K, little k. And then I have this bound on the misclustered nodes. So and the key term is here. So looking at this term, this tells me that, first of all, if I'm connected to more people, then this denominator is going to be smaller. So the degree does help, but at the same time, if I fix my degree, if this N2K here, which is the number of hub nodes in community K, if I know more powerful neighbors across all communities, then this denominator is also going to be smaller. So that's another piece of information helping you to do community detection, and that's reflected in our karate club example. And it turns out, if you recall this lambda mean, which we're proposing as a centrality measure for individuals, it also behaves like this term divided by n. So the same interpretation applies to this centrality measure. So now let me get to some simple simulation result. Yeah.
So do you recover the rate of the global community detection then if you have a very powerful node who knows everyone?
Oh yeah, so that's why we need to have the PN is defined as the maximum connectivity probability. So the PN has an upper bound, and in fact in these cases PN is going to 0, so we don't include.
PN always goes to 0, but like relatively, right? You can have potentially you can observe a network. You can have one node that just somehow so central. Frequency.
Yeah,
with this method, the way you're doing it, if it so happened, would it recover the local?
yeah, I think if you happen to have someone who can just almost observe all the edges in A, then this method should just work. Yeah, although that's not considered the out setting because this S and theta we conditional. These are high probability events and they don't include the case that you mentioned. Yes.
So can I rephrase that question? What if your node is such that the matrix A is equal to your matrix B? Does your algorithm reduce to the standard vector clustering, or is it a different algorithm?
If your B happens to be the full A, you can just apply the standard clustering.
No, but if you apply yours, is that the same?
From my system, I see. So, so if B is equal to A, then it's not rank 2K anymore. The population version is not.
Right, like in your example, right? You have an example where it just so happens that with L equals 2, you observe B equals to A. So that's the random version of the population. Could I just run spectral clustering on that B and I'll get the same answer?
We need to try. We actually haven't tried this particular algorithm on the full matrix A. Yeah, when we compare, we have some comparison with the full A, but we always ran the usual spectral clustering algorithm. Yeah, we can try it. Yeah, I don't think we have tried it. I think so. So yeah, I mean, for our method to work, you need to have the neighbors. I guess the neighbors will still have rank K. It's the non-neighbors. Yeah, I need to try it out. Yeah. But yeah, good question. We didn't consider that case because it's sort of ruled out by these high probability events that we can conditional. Yeah, so some simulation results. I'm generating a K equals 2 DCSBM, and the degree parameters are IID uniform, and this is the horizontal axis shows different values of n, and the vertical axis shows the misclustering rate, and these are different values of q. So we can see that in most cases it would converge. So here I'm looking at the performance of the centrality measure. I'm just generating one copy of the DCSBM, and I'm looking at everyone's clustering accuracy using their partial information network, and the centrality, and then computing a vector of centrality measures and a vector of clustering accuracy, and looking at the Pearson and the Spearman correlations between the two vectors. So I'm comparing with degree centrality, fraction of edges, eigenvector centrality between this centrality, and these are the correlations. So you can see that as expected, the lambda min hat, the empirical version, has the highest correlation. And I can also look at the correlations between each pair of these centrality measures. Sorry if you can't see these numbers here very clearly, but basically the other 4 types of centrality measures have correlations or very close to 1 in this simple synthetic network. And we have a correlation of around 0.7 with these, which suggests that we seem to capture a different model of information compared to these other 4 types of centrality measures. So I'd like to quickly talk about one different real data, not Karate Club again. This is a very famous data which looks at the diffusion of information about a microfinance program in Indian villages. And this the original data set analysis was published in Science. So they're looking at 40-something Indian villages and how information about microfinance diffuse throughout the village and the uptake rate of the program in the end in each village. So the social network in each village, we have households as nodes, and each edge is undirected in binary, representing any of the 12 relationships which they have collected in the survey. So there's borrowing, lending of money and material. And we have community labels. So what happened was in each village, they have a few predefined leaders serving as the injection points of information. So what happened was they called these leaders and told them about this program and asked the leaders to go back and spread information in the village. And then they look at the participation rate in the end. So we analyzed the 39 villages, and these villages are distant enough from each other so they can be viewed as independent social networks. And the number of households varying between this and the K varies between this. So the first thing we looked at is, so even though these leaders were predefined by their study using their own criteria, we wanted to ask the question, do leaders actually have a better awareness of global structure than non-leaders? And so here I'm plotting the clustering accuracy of the mean clustering accuracy of leaders in each village. So there's 39 points here. And anything lying above the diagonals is saying the leader does a better job on average than non-leaders in the village. And indeed, it seems like in most villages, they do have a better awareness of global structure. And here, again, I'm looking at correlation measures between clustering accuracy and different centrality measures using Pearson correlation, Spearman correlation, and between leaders and non-leaders. So these are the 4 groups here. I've added a centrality measure, the diffusion centrality, which was proposed in the original science paper as a measure to sort of look at how information spreads, how efficiently the information can spread in each village. So we can see that our lambda mean is still has the most stable and relatively higher correlations than the other overall higher correlations than the other centrality measures. And finally, I want to look at the correlation between this centrality measure versus the participation rate in the microfinance program. So again, each point here is a village, and I'm doing this regression of participation rate on the lambda mean of the leaders in each village. So the left one is our centrality measure, and the right one is diffusion centrality measure, which was proposed in the original paper to capture such an information. So we can see that even though lambda mean was originally designed for capturing information about community detection, it still seems to capture some useful information about the participation rate in the program. So just to sum up, we have introduced an individual-centered partial information framework to study the problem of community detection in social networks. We have derived the theoretical properties of the main signal term in the partial adjacency matrix, and we have shown some consistency results. And we have, in addition, proposed a centrality measure based on eigengap. So we believe there's still a lot of future work we can do under this setup. In particular, so far, there's this implicit requirement for consistency that we need to reach almost everyone in the network in order to get consistency overall. But instead, in a sparse network, we can consider what happens when I'm only interested in the membership if the individuals reached by the partial network. So I don't care those that I haven't seen in the network. So we can extend it to mixed membership, L equals 3, how to determine K, and what happens if our knowledge of the partial network deteriorate as we go away from the center. And we can think about putting multiple individuals' partial information together. And so I would like to just thank my collaborators again, and also Yi Qingxing, with whom we talked about the microfinance data. And of course, Peter, who has always been the beacon of light in my academic life. And every time I talk to Peter, I always feel I still have so much to learn from him. And he also gave us some very helpful feedback on this work. And with the last 1 minute, I would just like to do one little promotion of our other recent work, which again, Peter has given us a lot of feedback, suggestions, and perspectives. And the topic is quite relevant to this workshop. So we actually looked at the impact of core statistical theory and methodology papers on other scientific disciplines in the past 2 decades, so including the era of big data. And our paper is forthcoming in Patterns, which is the data science journal by the Cell Press. And we have the cleaned up data available in our code here. So if you are interested in taking a look and doing some further modeling of the data. And finally, happy birthday, Peter, and thank you for everything.
Thank you, Rachel, for the nice work. So we have time for one question. Yeah.
Well, actually, that's not a question. It's really terrific. One comment is that I have to admit, the first application of this that occurred to me would be, let's say, for the National Security Agency.
Yeah.
Terrorist network.
Yes, exactly. Yes.
The second thing is that there's some work which is unpublished of Sharma Bhattacharya, where he uses geodesics essentially to identify communities.
Yes.
And there might be some relation there. And if I may, a third comment is you make L equals 3 a stop. Well, that's true, of course, in any of the more or less dense regimes.
Mm-hmm.
But if you go down far enough, right, where your sparsity is just a little bit better than log n, let's say, for example, then you can pursue higher values of L, right?
Yeah, yeah. I think that empirically, I guess we need to look at bigger networks. But empirically, for example, the Facebook network, when we do L equal 2 or L equals 3, we almost already have that. But yeah, definitely, you're right. That we can look at that, at least in the theoretical analysis.
So talking about that, when I have square root of n average degree, after 2 step, I have sort of expansion proportional to n. So would you expect that if you have a general L, that the misclassification becomes good once you get n to the 1 over L? Because you would sort of expect that if the network is random enough, and you have n to the 1 over L a little bit more, then you should see essentially the whole network, or at least a positive proportion.
Mm-hmm.
And that should sort of be the threshold where you can do things or cannot do things.
Yeah. We are actually thinking about the threshold value like that, where we just have some rough calculations at this point about sort of the when this becomes very easy and when becomes very hard. And we are also thinking about maybe we're not interested in discovering everyone's community membership, and maybe it's okay to, if that person doesn't belong to my community, maybe it's okay to get it wrong. So yeah, we're thinking about extensions like that too. Yes, but thank you for the comment.
Thanks, Rachel, again. Yeah.